All right, so let me start with this one. We have this term here. So I want to determine first the gradient, directional gradient of psi. And because of the symmetry, you see psi can be identified with theta if I take cylindrical coordinates. R, theta, and z. Okay? These are the cylindrical coordinates, and it just coincides. So this becomes grad, the nu is normal to the surface of the cylinder, so I will take it ER, E along the unit vector along the R direction of this theta. And if I work out this, I just take the grad operator in cylindrical coordinates. So this is dr ER plus the grad operator 1 over R dd theta in E theta. And then the last bit, ddz along the EZ, which is just the z-axis, times that operates on theta, and then all this, because of the definition I gave you before of directional derivative, I take the scalar product with this ER, okay, with ER. So this becomes 1 over R. There is no dependence on this, then there is the dependence on theta here, and so we are left with 1 over R E theta, 1 over R dd theta, d theta and d theta is 1, E theta, and then this is scalar product with ER. So this is 0. Okay? So this quantity is 0. We are working on this one, and this is 0. Okay. Well, what about this one? Well, we saw that from definition, we saw that the Laplace of psi is 0. Okay, by definition, we took that psi, we worked out the divergence of the gradient, and this is 0. So this is also 0. So let's say this is 0. This is 0. Very good. Now we have to check on this one. If this is 0, this is satisfied. Okay, so we take that interval, and we call it I1, for example, and I have the integral of grad phi times grad psi in dv. Okay, in dv. And this is just a little bit going back to scalar to Cartesian coordinates. This is x d phi. I'm just substituting now the phi minus, let me complete, this is y dy phi, and this is over x squared plus y squared in dx, dy and dz, and this going back to cylindrical coordinates, that becomes the integral of 1 over r squared. You do your computation d phi d theta in r in dr, r d theta and dz. Okay? And then by computing that, you have z. Suppose that z goes from 0 to infinity. Maybe z, well, I took 0 and 1, dz, and then r. R goes from r0 to r1 cylinder, and this is 1 over r dr, and then theta. Theta goes from 0 to 2 pi of what? Of d phi, d theta, and d theta. But phi was assumed to be single valued at the beginning. So, because it's single valued, this is 0. So we are we can state that this is also 0. So this first version is okay. So 1 is okay. What about 2? About 2. Oh, about 2. Okay. Now, because of the multivalentness of psi, we have no guarantee that this is okay. So what we can write, we can only write the following. We can only write that minus the integral. We have psi is the tangent minus 1. I can leave it like that, or I can write it tan minus 1 psi over y over x, Laplacian of phi, of phi in dv plus the tangent minus 1 pi over x of the directional derivative along mu of phi in ds. We can only write that this is, in principle, different from 0. In principle. In principle. Okay. So we have to find a way to make sense of Green's potential theory in this case. So what we do is the following. We take our domain. There is a hole here. This is our domain, and we insert a cut. A cut. We want to simplify the domain, exactly as we learned from Riemann. So we put a cut here. A cut. And the cut along the cylinder. So the cut becomes this surface. Okay? This is a cut surface. Let me call it sigma. Sigma. And now if I take a cross section, in the cross section here, in the cross section, I have the situation where I have a hole, and then my cut here. Okay? And now let me, this is the situation. Now let me emphasize this situation by opening up the cut. No need to do that. Now let me emphasize that when I consider the cut like this, okay, like this, I can open up the thing, and I just emphasize that I have two additional part of the boundary to consider. One is this sigma minus, and the other one is this sigma plus. So the new boundary is, the original boundary plus these two contributions, as we did before. But now, when we do this, let's have a look there. You see, we have a volume integral, and the surface integral. Now, if I introduce a cut, and the surface domain has changed, then I have to correct this new contribution. So I have to consider this contribution, standard as it was, plus the new surface integral related to these new additional surfaces, sigma minus and sigma plus. Okay, so when I do this, the new boundary surface S, the new boundary surface S is the old boundary plus the sigma plus and the sigma minus. Okay, so the integral has to be over S, which we had, and then the other two contributions. So we have a minus, let me start from here, okay? I start from here, and I have from previous expression, we have. Okay, we have a minus the integral over the volume, tan -1 of y over x in Laplace phi in dv plus tan my integral over s tan -1 y over x of the directional derivative along u of phi in ds plus, now I have to compute, look, I have to compute this side along the new derivative over sigma 1, sigma plus, and sigma minus. Now, let's go back to our cut here. And we take, for simplicity, I didn't put it there, but I can take for simplicity a reference system along this cut, like this. So I take this is x, of course, this is z, and to some extent, here, somewhere, I have y, okay? If I take, so this is x, and this would be y in the cross-section plane. So the normal contribution is nu. The normal contribution to sigma, to the cut sigma, would be for sigma minus along minus y in this direction. I will have one contribution in this direction, the other contribution in this direction. This nu, in the new surface boundary, then we'll have these two contributions. Okay, and then what about tan -1? Tan -1 would coincide with theta in cylindrical coordinates. And theta would be when I move from here in this direction, would go from 0 to 2 pi. Okay? From 0 to 2 pi, because I identify psi, which is tan -1, with theta. Of course, this is the definition of theta in going back from Cartesian coordinate to polar coordinates. So there is a contribution plus a contribution when theta is 0 from tan -1. When theta is 0, there is 0 contribution. When I go back to 2 pi, there is a contribution. So I have a 2 pi that comes out times where I was, I'm here, 2 pi, the integral, I have 2 pi comes from tan -1 now, because I'm going from there to the other side. And now we have to consider this directional contribution along nu. Now along nu is either along y or -1. So we have now the gradient directional along, say, the j, the unit vector of y, of phi calculated at y equals 0 in dx dy. Now, tan -1, because of the cut, is now continuous. So this is exactly what we have. Is that this is now satisfied. So if you like, we have a 0, remember, from where we came, the 0 equal to this. This was a standard way for Kelvin to understand what is going on in the case of a hole. And this standard way, at that time, to understand things in some kind of generality, starting from one example. So I like, so first of all, this 2 pi is a constant. So Kelvin noticed that this comes from a kind of circulation of psi around the hole. You may think of a contribution from the hole, from the presence of a hole. So I propose to generalize, now these are my words, to the following. We consider a manifold M. Of course, you need some properties. You need that it is compact, because you want all functions to be convergent at some point. I don't want to spend time much on mathematical definition. And consider a manifold M that is compact and but if you like multiply connected with a number of holes with G holes. G has a name now because of the contribution of an Italian topologist to this. He became friend of Riemann. Riemann had a short life, and he was severely ill by tuberculosis, and many members of his family died earlier in life. Anyway, he was recommended to move to a better climate, and so he left Germany to move to Italy. And he passed away in Italy, and is buried in Italy, in the north of Italy, near Milan. And moving to Italy, he became to know personally a number of great mathematicians. One of them was Betti, and Betti gives the name to this number of holes. So G holes, and G stands for the Betti number. Is the number of holes we have in a manifold. So suppose we have a manifold in general, and there are a number of holes here, and okay, these are G holes, and G is a Betti number, or the first, it doesn't matter, but the first Betti number. And if we deal with that, so we can say we have a kind of lemma or theorem, and let's attribute this lemma to Kelvin, although are my words, 1869, I couldn't have written something like this in 69, but anyway, a multiply connected manifold, compact manifold M of Betti number G, volume V, and boundary surface S, can be reduced to simple connectivity by the insertion of G, this time on surfaces, cut surfaces multi-dimensional surfaces. Sigma I, where I goes from 1 to G, the number of holes, so that the green potential, the Green's first identity for the multi-valued potential psi associated with say the field U as phi grad psi, where for simplicity phi is taken single value, on M becomes, you can generalize this result, the result that we just found through the correction of the cut surface, of a single cut surface, to a number of cut surfaces, to simplify the connectedness or the connectivity, as it's called nowadays. The following, we have, of course, grad psi dot grad phi, and this is psi plus psi, a Laplacian of phi, and this is standard volume integral. This becomes the integral on the surface without the cut, so to speak, psi, directional derivative of phi in ds, plus the correction term. We have this correction term. Now, the 2 pi is just a constant, so we can associate to each whole a constant. So we have a sum I that goes from 1 to G, number of holes, of constants Ki, integral of the grad along the new surface, or better, the cut surfaces inserted, sigma i's, of phi in ds. So this generalizes the Green's potential theorem, where each kappa I, Ki, is the, I call it the potential strength, is the potential strength associated to each hole present in M. Okay, so I attribute this statement to Kelvin for obvious reason, because it's due to him to find out this correction term, but evidently, he didn't manifest this as a lemma, as a theorem in this form. I mean, the study of a manifold with the number of holes came with Betty, so we are much later in time. It cannot have been done by Kelvin. We're talking 18, I can't remember Betty work. Maybe I've written it somewhere. Let's see if I wrote somewhere a note of that. 1871. 1871 was the work of Betty. And then, so many years from the late 50s, 20 plus years when they met. And well, actually, Riemann passed away in 1860 something, 66 maybe. I can't remember, 66. So, and Betty, there is a beautiful letter, by the way, of Betty explaining what he learned from meeting Riemann. Okay, so this is really at the beginning of the explosion of topology. Remember, topology at the time of Riemann didn't exist, and so that was the first contribution, really, apart from Euler. And then Gauss, as I mentioned, and then it became an area of research with the work of Poincaré in France, and but we are already towards the end of the 19th century, right? So, and then kind of developed gradually. Now it's booming. Now is really a research area of importance for physics. So in the time left, I want to tell you something, not much of mathematics, just a little bit of physics, to tell you that for a number of years, we have two things here, two ingredients, if you've noticed, among many. One is the role of potentials, being multivalued or not, blah, blah, blah. And the other thing is topology, the idea of halls. Now, topology, as I said, was not an important subject in mathematics, was just germinating new stuff. But even in the last century, in the 20th century, for some time, potential theory was regarded as a mathematical artifact. Physicists were really reluctant to talk about potentials. And it makes, to some extent, it makes sense. You measure in gravity, you measure gravitational force. You do not measure the potential between two points. There's no way to measure it. You measure forces. Forces, if these forces are conservative, are expressible in terms of a gradient of a potential, but you do not measure potential. Potential was regarded as a mathematical way to describe physics. Then became a proposal from physicists. And the proposal goes like this. We have Aronov and Bohm, that in, let me see, in different, that in 1959, proposed an experiment. So it was on paper. It was only on paper. And the experiment was like this. Now, imagine that instead of your vortex tube, instead of vorticity lines, you have a magnetic field, B. And there is, how to say, B different from zero only inside the tube as vorticity. And as vorticity, zero outside, here, B, zero, exactly. Remember, we were in the same situation with vortex filaments of Kelvin. Vorticity different from zero here, vorticity equal to zero there. Now, B can be written as the curl of A, as we did for vorticity, the curl of U. And this is the so-called vector potential. I like to draw your attention to an analogy between fields, because it helps to fix ideas. Analogy between Euler flows, ideal, inviscid, eventually incompressible, etc. And what we call ideal magneto hydrodynamics. And this analogy goes like this. In Euler flows, we have vorticity, vorticity. Omega curl of U. Then we have the transport of vorticity. Transport equation for vorticity. It is called Helmholtz equation. Is d omega dt equal the curl of u cross omega. And then we have a quantity that is conserved, is invariant of ideal fluid mechanics, that is important, and is called kinetic helicity. And this is the kinetic helicity hk, and this is the integral of u dot omega. Okay? All right. Now this system is made equivalent to the ideal MHD, magnetic hydrodynamics, when we take the magnetic field B, which is the curl of A. A has the name of vector potential. And then we have the transport equation. Transport for B, transport equation for B, and this is called, you should know, is called Faraday's equation. From Maxwell's equation. dB dt equal the curl of what? U. Yes, there is the same U, but here we have B. So it makes, here the relationship between U and omega is established like this. Here the relationship between U and B is not established by any particular law, except the one you prescribe outside this system. And then we have magnetic helicity, and this is HM, which is A dot B in dV. These two quantities, helicities, are quite important because are conserved like energy in ideal motion, ideal flows. So they play an important role. Okay, so what happens to the Aharonov-Bohm proposal? Well, the Aharonov-Bohm proposal is the following. They considered the case, let me give you a little drawing. Let me draw here in a very simple sketch what I have in mind. So the magnetic field is totally confined. How do we realize this in the lab? I saw it with my eyes. You think, you take a solenoid, and you have high current flowing in the solenoid. So imagine the solenoid is like a spiral, like this. Tighten up, okay, very tightened, so there are much thinner pitch of the helix, all tightened up, and the magnetic field is generated inside, like this. So the end result is a magnetic, magnetic flux tube. What's a vortex? What's a vortex? Where the B lines are different from 0 here, and B is exactly 0 outside. If you induce a high current, then the field is totally confined there. Now, of course, you know, B has no monopoles so far, so it means the divergence of B is 0. It means that this field may close on itself, but if the current is very intense and is sufficiently long with the solenoid, then the field closes on itself far away. So a particle here doesn't feel any field outside. Now what we do here, we put an apparatus, something like this, some box, something like this, and then we shoot on one side, we shoot electron flow from this side. And on this side here, we have an apparatus, interference device. Okay? Now, what happens to the particle flow? The electron particles are moving here, but then they are deflected by the presence of this intense magnetic field. If it is sufficiently intense, they do not enter the solenoid or the field, so they go round like this, and then they keep going like this. So they go like this, they go round, and then they recombine. Now, all going like this, and all going like this. Now, in classical physics, you cannot detect any difference. But in the quantum context, the path followed by A, like the vector potential, is different. The path of the vector potential along this side and along the other side are different. And so because the flow of electrons started coherently, it is detected an interference between one flow in one part and the flow in the other. So experiments started, went on. Of course, as usual, were a lot of discussion, dispute, differences in measurements, etc. But the thing was settled for the positive. In other words, it was settled that there is an influence of the presence of the magnetic field in the domain with respect to the flux. Here you measure interference between vector fields, between potentials, so to speak, or wave functions associated with these potentials, and the difference in intensity of the measured amplitude of the sum of the contribution from the wave functions gives you a relationship with the flux of the magnetic field. So if you change the flux, you change the interference pattern. If you annihilate the flux here, no magnetic field, no current, nothing, then you change the interference pattern. There is no interference. And this was, I can quote a beautiful kind of review of this situation, for physicists. I read it a long time ago. I might have a reference here because it gives you also the little bit of history. So the group of Tonomura et al. In Japan, they wrote a beautiful kind of many people. Actually, this paper is another one. Probably is a physics review letters when they report the result of their experiment. Is issue 56 and is 1986. I remember I read a beautiful review in Physics Today, and this is the original paper, so you can go for and check yourself. So there is a kind of recollection of other previous results and the definite proof of the Aharonov-Bohm effect. So the Aharonov-Bohm effect establishes the influence of the, let's say, topology of the ambient space in terms of measurable physical effects. Physics. Okay? In terms of measurable effects. That was an important result for those of us who do mathematical physics and theoretical physics in particular. For mathematical physics, it convinced a number of people that really topology had a role to play. We are already 86, so we are well into the time where people in high energy physics, just to name string theory, Edwin and others, were already doing work on topology and physics. Our Kelvin, thinking that the topological complexity of the localization of energy, fundamental level, was saying something in terms of physics, of fundamental laws of physics. So you use topology to understand the physical effects of topology. Here you have a space, you have a hole in the space, or the presence of this obstruction that plays the role of a hole for the electrons. Same thing. So you see, you can work out all these presentation in words. You can do some mathematics on this and exactly use the cut surfaces to come up with the right result. So you can do this. I won't repeat it because I used the Kelvin's example as in fluids, as intuitive and mathematical reason for this. But it's the same thing. It's the same thing. Now, because of the analogy there, you see, I introduced some invariant, not energy, but helicity. And helicity, I mentioned, plays an important role in modern magnetohydrodynamics. So before finishing, I want to consider also helicity and magnetic fields in another context. Why? Well, here the role was actually played by the vector potential, A. The vector potential played the role. And when I think of other contexts, I will give you an example now. Again, the vector potential plays a role, but where do we have systems that are topologically non-trivial? Physical systems that are topologically non-trivial. I mean, this is topologically non-trivial because the magnetic field induces an obstruction from the electrons. But there are systems that in front of us are topologically non-trivial of any scale we like. Let's say, for example, the human scale, or in nature, in cosmology. Let's consider the magnetic field confined in a torus. Well, that is an example of a domain for the magnetic field that is topologically constrained. Because the torus is, it's a big torus, magnetic field. Let me use this word, confined in a torus, toroidal domain, torus. Okay, we have torus like this, and magnetic fields like this. If you think of substituting magnetic field with vorticity, you have a vortex ring. Now, this torus can be built, and I'm sure you know what I'm thinking of. I'm thinking of tokamaks. Tokamaks for fusion, for fusion research, or for fusion energy, of course. So there's a plasma, highly conducting. Remember, in Euler equation, invisible, no dissipation. Here, almost infinite resistivity. And in this situation, you confine, because there are toroidal coils everywhere, currents, intense currents, you confine the magnetic field as you confine the magnetic field here. So you have this situation, you close up on itself, and you build a machine like this, right? And then you have your plasma going in this machine, and you want to control many things, and of course, you want to get to some parameter space in which you have a given very high temperature, given pressure, and density, so that you ignite the fusion process to extract energy from the input energy. Okay, leave aside technology and applications because I don't know much about it. I just want to show that this is a physical machine that is topologically non-trivial. It has a hole in the middle. Now, can we apply something we learned today to evaluate some of this information? Well, as a matter of fact, this is my last contribution to you, and I want to discuss this. So the theme is magnetic helicity in multiply connected domains. Okay, tokamaks G, number of holes, 1. Of course, the torus. All right, so I want to do this. I believe not many of you know about helicity, and I would like to tell you at least a few little things just to set the scene properly. And I work on helicity myself during starting my PhD on this under Keith Moffat, and Keith Moffat gave a very fundamental contribution to helicity by interpreting this quantity in terms of topology, in terms of linking numbers. But we need a definition. So let me say that, the definition is there, is a definition, let's say. Definition is in simply connected domain the magnetic helicity, what I wrote there, the magnetic helicity, HM, integral of A dot B dV, where the magnetic helicity is given by, given by that, where B equals the curl of A. We take A, we usually take A to be the Coulomb condition. Div A equals 0, this is pretty common, where B is, of course, the magnetic field. Is the magnetic field in the magnetic volume, V, such, for a proper definition, this is a volume integral, such that we have B dot nu, remember nu is the normal to the boundary of V, to be 0 on S, boundary of V, and this surface is a magnetic surface. Now, for a tokamak or for any other magnetic domain, that means that the magnetic field has no flux through the surface, because it's always tangential to the surface. No flux of B through the surface. Okay, so this is the definition, and then we can just state as a theorem, no proof, just mentioning it in ideal MHD, magnetohydrodynamics, the magnetic helicity HM is a conserved quantity in time. So that means that ddt of HM is equal to 0. HM constant in time. Okay, this theorem is due to Ochi. 1958. So HM is like energy for Euler flows, kinetic energy, totally conserved. It's like linear momentum, is a new conserved quantity in fluid mechanics. Maybe it's not so mentioned now in standard books because it was proven conserved only in 1958. Well, it's already 60 years. It takes time for books, textbooks in particular, to acknowledge that. And as I mentioned, I will not talk about that, but as I mentioned, the proof that came from Keith Moffat in 1969 was to express this quantity in terms of topological terms, linking numbers of Gauss. So there is a connection with topology, fundamental connection with topology. I won't mention this. I just want to remark that being a conserved quantity in ideal MHD, it is almost conserved in this plasma physics situation.
Sir?
Yeah?
It's a general question, but in fundamental level, we know from the analytic table, if we have some conserved quantities, so we must have some continuous symmetries behind the conserved charges. if there is any symmetry, if we explain this term in terms of symmetry, so how we can link up this term with symmetry?
Yes, I give you an idea, and the idea is you have a velocity. I go back to velocity and vorticity. It's the same thing. A and B is the same thing. So if this is the velocity field, let me go back to vorticity. If this is vorticity, you have a velocity going like this. So you have a linkage between this line and this line. Okay? If there are no dissipative effects, the linkage between this curve and this curve is unbroken.
Yeah.
That is the conserved aspect in, you can interpret that as the conserved aspect in Noether theorem. Yeah. So it's a kind of helical. You relate the helical particle path of the fluid with the vorticity or the magnetic field. So using Noether theorem, you can prove that by just relabeling technique on particle path, and this is the meaning. The linking is preserved. So this is a kind of symmetry you have. Is a more abstract than just a rotational or a translational symmetry.
Because I didn't heard this type of hazard charges
Of course.
before, so that's why I'm a little bit like.
Of course. And mind you, just because, well, I'm not an expert here, so I apologize if I go beyond my knowledge, but I just like to remind you that there is a term, helicity, used in quantum mechanics.
Yeah, helicity
is not the same thing.
Oh.
Okay? Because in quantum mechanics, helicity is related to the spin and the projection of the momentum, of the spin and the momentum. And now this is, the projection of the spin and momentum is a scalar quantity, has no topological meaning.
Yeah.
No topological meaning because there is no constraint on the fact that the spin determines something close, the link with the momentum. That doesn't make any sense.
Yeah.
So in quantum physics, the term helicity was introduced, I believe, much earlier than this term in fluid mechanics. And the two communities didn't know each other usage of this term for a long time. Now it becomes clear that one community uses this term, but is not at all the same. Helicity in field theory, in this context in particular, hydrodynamics, has the topological meaning of linking numbers. Simply because we assume that the divergence of B and the divergence of A are zero. So we mean that these field lines are closed and they link to one another. Similarly for the divergence of the velocity and the divergence of the vorticity. Divergence of vorticity is zero because it's the divergence of the curve. So it has to be zero. Okay, so that's it. So yeah, thank you for the question. Now, all right, we are in this situation now, and we want to work out eventually if there is a correction term to magnetic helicity. So let me do, I'm just playing a little bit with symbols here. Let me do this. I want to rewrite this. You see, there is a relation between vector potential and B, like so. So now let me write the new. It's just convenient. Let me write the new vector potential. A has one part that is rotational and one part that is irrotational. The rotational part, curl of AR, is evidently giving me B, The irrotational part, AI, is not giving me anything. Okay? So it's just a decomposition of this A. So helicity in this terminology is just, of course, the AR B in dV. Okay, it's just a calculation of the rotation. All right. Now, because of the multiply connectedness, we are dealing with potential again. A is the potential for B. So it's again potential theory. And because of potential theory and because of the use of potentials on manifolds like a torus that has a hole, the potential are multiply valued. So we have to cut, to simplify this, as we learned to do before. So a new cut intervenes. Well, let me take a cut through the domain of the magnetic field, not the whole. So, I assume, for simplicity, that we deal with a torus that has a cross-section that is a disk. So this is my cut surface. Okay? Okay, this is a cut surface. Sigma. And again, you may think, no, we know what I have in mind. There is a sigma minus and a sigma plus, because we are now opening up this torus. It becomes like an infinite cylinder, topologically speaking. Okay, so what happens to these contributions? Now, consider we take this coordinate, we call it a lambda. And this coordinate, this is a longitude. The two coordinates for the torus coordinates, there are two coordinates. One is lambda, the longitude, and the other is mu, say something like this, mu, and it is meridian. Okay. All right. So we have an integral of AI, irrotational part, along lambda. Lambda is a closed line, and this we express now this potential, the vector potential, in terms of grad, and we have the integral over lambda of this grad of phi I. The potential associated with this vector potential, scalar function phi, and this is the jump of phi when we go from sigma minus to sigma plus. Okay? So this we can call it H. Alright, and now we calculate helicity, Hn. Now helicity is defined as AI and plus A R, everything in B, dV, and this is the integral. Okay, we use using div B equals 0, we have. Okay, now AI, we substitute with this grad, and we have a divergence of B is 0. We put together this and this condition here, and in place of AI, we have the divergence of phi I times B, and this is in dV, plus the other term, AR. So the other term is the integral of AR. This is the rotational part times B, but B is the curl of AR. Okay, this is just the definition. of helicity as we had it before in simply connected domains. Now let us consider the first integral from the right-hand side. And we have the integral of the divergence of phi I b. Okay, dB. And this we use, okay, this is divergence theorem again, because it's the divergence, we use Gauss again. So we can convert a volume integral to a surface integral, S, and this is phi I BDS, and this with the cut. So the S becomes now an S prime. S prime is just the S, the old S, union sigma, or if you like, sigma plus and sigma minus. Usual stuff. So we modify the boundary, and here we have a delta phi, the jump from one side to the other of phi times the integral of b in ds. Okay? And as usual, remember that S is just a surface times the unit normal to the surface. And this is delta phi is h, we call it h for simplicity, somewhere, I don't remember where, here. So this is h integral of b in ds. Okay.
So is these both integral variable the same? Because we want to integrate over S prime.
Yes, that's right.
So
yeah, it would be on S prime.
Yeah, so
yeah.
Is it same or it should be S?
Yeah, for me, you know, this is I've integrated already here on S prime. If you like, it's an S prime here. It's just the element of the surface. But now it's extended to S prime. Okay, so we are done because we can write now. We can write now that Hm is now given by the integral of A dot B as we used to have, plus H integral of B ds, and this is extended to the sigma, sorry. Yeah, what you were. Okay, so in general, so if the domain of B has G holes, we have a generalization of this, the helicity Hm becomes integral of A dot B as we used to have for simply connected domains, plus the sum extended from I1 to G of these H constants times the integral of B in ds. And this is extended to the cut surfaces sigma I. Okay? And which bears an analogy with say, the generalized correction term of Kelvin. Hi can be thought of a potential strength. Of the ith hole of the ith hole. Sorry. So I hope to show you application of Riemann's cuts in a modern context. I discussed this in the case of a vortex tube, in the case of a magnetic tube, when they form configurations that are topologically non-trivial in the presence of holes, etc. But I want to remind you that these techniques or this technique, Riemann's cuts, has found applications in other contexts. I can mention just a couple of my own works, but of course there are many other works. By direct experience, I can tell you, consider now the presence of defects in condensed matter physics. Defects, so we are in a case where condensates have been produced in the lab. A number of Nobel Prizes came after the discovery of condensates in labs between late years of the last century and early this century, well known in particular condensates as Bose-Einstein condensates. And what we have in condensates, so you go to extremely low temperature and you have a gas of, for example, well, it's typically a gas of bosons, so for example, photons, or, reminds us of the models of black holes. And you may have a defect. These defects have been realized in the lab already. And what is a defect? Well, as the word says, a defect is a lack of particles in a particular point in space. So we may have defects like tubes in the condensate. These have been done, have been seen. And these tubes are very interesting because they are, they are empty cavities. So imagine you have a little tube in a condensate, so there are particles everywhere except in this tube. But this tube thickness is extremely small. And it's like a filament made of void, no particles. So, because of defects, they represent a complexity in the connectivity of the ambient space. So they are providing the ambient space, i.e. the bosons around, topological connectivity. And this connectivity can be high or small. Can be small in the presence of one defect. You can have a one vortex ring defect. Why I call it a vortex? This is another issue. Very interesting. Because this is totally empty. Nothing in it. There is no vorticity in it. However, if you measure circulation here, you find circulation. Oh, wait a second. You have a velocity that has a circulation, but the curl of the velocity is 0. How that makes sense? So that intrigued me. This is one question. This is one question. It's good to make to emphasize this. Sorry for the noise. Defects in condensates. For example, BECS, e.g. BECS, Bose-Einstein condensates. So you have a defect and then the condensate all around. Point is, as I said, you have a velocity, u, and this velocity, here there is nothing. So this is a cavity, empty cavity, empty tube, which is a defect. A defect. And so the curl of a u is exactly 0. Is exactly 0. There is no vorticity. However, you have circulation. However, we have circulation, say gamma, different from 0. And even more, and quantized. So it's very strange. Curl of u is 0, but gamma is different from 0. How is this? So in books, in standard books, when you use a hydrodynamic approach to this problem, you find these statements. You find the statement that this gas is like a fluid. Of course, it's not the same, but it's like a fluid, and you can convert the equation that controls the condensate. For example, Gross-Pitayevsky equation, you can convert it to almost Navier-Stokes equation, Euler equation plus a momentum equation. So it behaves like a fluid. You can study it as a fluid, and indeed they do, by using hydrodynamics techniques and by using simulations techniques developed for real fluids. You study these things, but these things have this property. Two things strange. One, the curl is different, is 0, but there is circulation. And the other thing is that circulation, not only there is circulation different from 0, but it's quantized. How is it possible? Well, I fixed this problem with collaborators in a couple of papers by using Riemann's cuts. Again, you have to use Riemann's cuts here. You have to redo your calculation. You place a cut, and somehow this is in space. Somehow this is in space. You open up the domain. Then you do your calculation, and you prove rigorously, first of all, that velocity u. The velocity u cannot be written as the grad of, say, some potential, but has to have a contribution coming from Dirac delta on sigma, on the cut. And when you do this, that makes sense of this and makes sense of other stuff. And when you use the cut, it makes sense that you have a quantized circulation, because with the cut, it depends on the number of times you go around and you go across the cut. So you can give meaning to the fact that the curl of U is equal to some vorticity, but this vorticity is like a delta Dirac vorticity as a Dirac delta function. So that when U is grad of phi, all this makes sense because you have now a Dirac delta function there, and when you integrate, you take into account of the Dirac delta, it makes sense to have a quantization of circulation. So this is just an example, and this is published work of, say, 2 or 3 years ago in defects. But then, as was mentioned, there are many aspects of physics. You have, I'm not so expert on this, you have magnetic flux quantization, as you have here. You have liquid crystals, in which topology plays a role. You have systems with spontaneous symmetry breaking. Similarly, now there is a big theme of topologically confined systems, systems in which topology of say, as it were, a defect or something else is confined. It cannot change to another type of topology unless you change the boundary conditions. And this has incredibly interesting aspect for lots of applications in technology. For example, quantum information, communication. You know, you want to send an information and you want to receive the same information. This invariance of the information, you can read it out as a topological aspect. You want to send some form of signal that whose topology is preserved and is carrying information through topology. Otherwise, the opposite is also possible. You want to have this defect interacting and producing turbulence, noise. And this this quantum turbulence has many properties similar, we are talking microscale here, to the classical turbulence of classical physics. And turbulence in quantum system is also very interesting. You can use it to encrypt signals or decrypt signals and so on. So, plus all the applications, as I said, in not only liquid crystals. Let's think of biology, polymers that get knotted, and surfaces that change the topology or preserve topology according to the functions. So there is now, as I mentioned at the very beginning, the knotted fields book that we published is a collection of contributions that gives you this perspective. So I invite you to read or have a look at the Monastirski's book on Riemann, because it has 2 parts. One is dedicated to Riemann's work, and the other part is related to the physics of the 1990s. And then the Knotted Fields book that we just published almost 20 years later or more, that gives you a perspective of modern trends in topological field theory that are really extraordinary in their width of variety of topics, including, of course, not only high-energy physics, but also the other extreme, black hole cosmology, multiverses, all sorts of strange things that are going on in theoretical physics nowadays. So thank you for your attention. That's all.